This video covers Unit 2, Part 1, Matter and Energy, the first portion of classification, states, and properties of matter. We will cover the first 3 learning objectives in this video. Please take a moment to pause the video and read through them before we begin. Matter is what all things are made up of. All the materials, some of it we can see and some of it we can't see. And matter is anything that has mass and occupies space. Matter can be broken down into 2 different forms, pure substances and mixtures. What form of matter do you think we encounter most in our daily lives, pure substances or mixtures? Why do you think so? We'll take a look at this information. We'll take a deeper look at both of these in a moment. So pure substances can either be elements or compounds. Elements are made up of one or more of the same atom, whereas compounds are composed of 2 or more elements chemically combined. Notice that we've got aluminum here and copper. Notice that we've got aluminum and copper in a penny and a can, and is made up of all one type of atom. Whereas water is a compound, is made up of 2 hydrogens and 1 oxygen atom. So let's look closer at elements. Remember, elements are pure substances that contain only one type of atom. They cannot be separated by chemical means into simpler substances. So an atom is the smallest unit of any element that maintains that element's physical and chemical properties. So far we've had 118 elements that have been identified. Some of them have been created in the lab by scientists, and some of them are naturally occurring. Compounds now contain 2 or more elements in a definite ratio. So for example, we've got hydrogen peroxide, which has 2 hydrogens, 2 oxygens, sodium chloride, which is table salt, glucose, and water. These can only be separated into their pure components or elements by chemical means. What are some other compounds that you might come across in your daily life? What are they used for? Mixtures are a combination of 2 or more pure substances. Now, in a mixture, each one of the substances maintain their distinct identities. They are not chemically combined to each other, and a mixture can have a number of different proportions. The one thing about mixtures, though, are that they can be separated by physical means. What do you think of some ways you can separate a mixture? Think of some of the common mixtures you come across daily. How would you separate a mixture of sand and water? Well, you can use something like this funnel set up here to separate a mixture of sand and water. How do you think you might separate a mixture of salt water? Have you ever gone to the beach on a hot day, and at the end of the day of the beach you have these lines of salt on your skin? Well, that's because all of the water evaporated and the salt was left. So to separate that salty mixture, you simply have to get rid of all of the water. There are 2 different types of mixtures. There's a homogeneous mixture, and there are heterogeneous mixtures. Homogeneous mixtures have the same composition throughout, whereas a heterogeneous mixture does not have the same composition throughout. So a bottle of Coca-Cola, maybe mayonnaise, let's say French dressing, those will all be like homogeneous mixtures. Whereas something like where you can see the different components would be a heterogeneous mixture. So, how do we classify matter? Well, matter is classified either as a pure substance or a mixture. If it's a pure substance, we have either elements or compounds. If we have a mixture, then we have a homogeneous or heterogeneous mixture. So how do we know how to classify matter? Well, are the properties and composition constant? If yes, then it's probably a pure substance. If no, it's probably a mixture. And the way that we can separate this mixture is by some type of physical process to get each pure substance by itself. Now, if we have a pure substance, is separation by a chemical reaction into a simpler substance possible? If so, that means that we have a compound. If not, that means we have an element. And to get between a compound and an element, we have to have some type of chemical change occur. Now, if we're looking at mixtures, is the mixture uniform? Well, if it's uniform, then we've got a homogeneous mixture. That mixture is not uniform, then we have a heterogeneous mixture. Let's do some practice. Distinguish between the mixtures and pure substances and classify pure substances, elements, or compounds. That's our learning objective. So number 1, identify each of the following as a pure substance or mixture. You go ahead and classify pasta noodles, aluminum foil, helium, and air as a mixture of pure substance. Pause the video and classify them. And when you start the video again, we'll go over the answers. Okay, pasta noodles are a mixture. We know it's got flour, water. Flour is made up of a number of different compounds, so it's definitely a mixture. What about aluminum foil? Aluminum foil is a pure substance because it's made of only aluminum. It's all aluminum atoms lined out, pressed out in a nice sheet. What about helium? Well, helium is a pure substance. Can we classify that additionally? Let's see. Air is what? Is it a pure substance or a mixture? Correct. It's a mixture because it's made up of carbon dioxide, oxygen, nitrogen, and other trace gases. Can we further classify these mixtures as either homogeneous or heterogeneous? What about pasta noodles? Would you consider them, let's say we're talking about plain regular old pasta noodles, not wheat pasta noodles. What would they be considered? Heterogeneous or a homogeneous mixture? Right, homogeneous. What if it was those wheat pasta noodles? Yeah, that would be a heterogeneous mixture because you can actually see the wheat flecks in the pasta. What about air? Is it homogeneous or heterogeneous? First off, can we see the air? Can we see the different composition of the air? Nope. Well, then that means it's a homogeneous mixture. Let's go ahead and try number 2. You go ahead and pause the video and answer the question. Identify each of the following as a homogeneous or heterogeneous mixture. And when you come back, we will go over the answers together. Okay, a hot fudge sundae. Well, we can see all of the component parts, so it's a heterogeneous mixture. What about body lotion? It's a homogeneous mixture. We don't see any of the components that are in that lotion. We just see whatever the color and plain simple lotion in the bottom. What about sugar water? It's also a homogeneous mixture because we can't see the different components. What about peach pie? Yep, you slice it up and you see the peaches, you see the crush, you see the juice, so it's a heterogeneous mixture. Let's try some more practice. A white solid with a melting point of 730 degrees Celsius is melted. When electricity is passed through the resultant liquid, a brown gas and a molten metal are produced. Neither the metal nor the gas can be broken down into anything simpler by chemical means. Let's classify each as a mixture, a compound, or an element. So we're looking at the white solid, the molten metal, and a brown gas. Well, the white solid has a melting point. And it says when electricity is passed through it, we end up with a if we pass so we melted it, it's got a melted point, it's a solid, it becomes a liquid. And once we put electricity through that liquid, we end up with 2 more products. We end up with a molten metal and a brown gas. If we have something that can be broken down by chemical means, such as an electrical current, is that considered an element, a compound, or a mixture? What could we say about that white solid? Think about that as we continue to read through. The next thing, it says that neither the metal or the gas can be broken down into anything simpler by chemical means. Okay, so let's think of this white solid. First, it says it's got a melting point. Well, that is a physical characteristic that helps us to identify a substance. It says that when we pass electricity, we cause a chemical reaction to occur, and we end up with a gas and a metal. So what is that white solid? Is the white solid a mixture, a compound, or an element? Well, it's one solid, and it goes from a solid to a liquid, and then it's broken down into chemical means. So we can call that what? Not a mixture, a compound, or an element. Which one do you think? It's a compound because we can break it down by chemical means. What about this molten metal? Notice that it says that neither the metal nor the gas can be broken down by chemical means. So if it was a compound, we would be able to split that compound into their component elements. So are these an element or a compound? Well, since we can't break them down into something simpler by chemical means, both of these are elements. Let's do some practice. Which of the following is a compound? Pause the video, answer the question, and you come back, we'll get the answer. Table salt is considered a compound. Milk is a mixture made up of a number of different proteins, sugars, fats, all those things, so it's a mixture. Aluminum foil we know is an element because we know that it's made up of only aluminum atoms. Silver is the same way. It's an element. It's going to be made up of all of one type of atom. Let's try the next question. Pause the video, answer the question, and we'll go over the answer together. Which of these is a mixture? Sodium metal, solid sodium chloride dissolved in water. Well, sodium metal is an element, so that's not a mixture. Sodium chloride is a compound, but if we have sodium chloride dissolved in water, we've got sodium chloride plus water. Remember, a mixture is anything that is two or more pure substances put together. So what's our answer? C. Only sodium chloride dissolved in water is a mixture. Let's try the next question. Pause the video, answer the question, and we'll come back and answer it together. Which of the following is a homogeneous mixture? What did you put? Correct. Lemon flavored water. All the rest of the substances that we are looking at is a heterogeneous mixture where we can see all of the different components. Lemon flavored water, you add a little bit of flavoring to the water. The flavoring is made up of compounds. The water is a compound, and we have a mixture. We can't see the difference in the mixture, so it's homogeneous. Elements and chemical symbols. So if we take a look at elements, we know elements are pure substances and they can't be broken down into simpler substances. The chemical symbols help us to represent what each element is. Now, a chemical symbol can either contain one or two letters. If it has two letters, it starts with a capital and it ends with a lowercase letter. Notice that we have our one-letter symbols such as carbon, nitrogen, fluorine, oxygen. And notice over here we have two-letter symbols such as cobalt. Notice that the second letter is a lowercase. If I have two capital letters next to each other and they're representing elements, know for a fact that it is a compound. It is not an element. An element has to have, if it's got a two-letter symbol that's a capital and a lowercase letter, it's going to be one element. What are some of the pure elements you come across in your world? Did you think that ring that you're wearing on your finger is 100% gold? Ha! It's probably not. Check it out. 18 carats, 24 carats is considered 100% gold. Are you wearing 24 karat? I don't know. All right, here are some elements and elements that are essential for human life. Notice we've got the four major: carbon, hydrogen, oxygen, and nitrogen. A number of these other elements are are used for different parts of your body, different things. These chapters don't represent our chapters in our textbook. But notice that these elements are all really important for us to use in our body. So this says down here, other elements listed vary in their distribution in different foods. Those marks with an asterisk are macronutrients, meaning that they're essential in the diet at more than 100 milligrams per day. The rest, other than carbon, hydrogen, oxygen, nitrogen, are micronutrients, and they are essential at 15 milligrams or less per day. Here are some common elements and their symbols. These are a number of the symbols that are common. You should be able to know or memorize up to 20. Some we will use often, but notice that if it's a 2-letter symbol, the first letter is capital and the second letter is lowercase. Let's do some practice. Write the correct chemical symbols for each of the following elements. Pause the video, write down what you think the symbols are, and we will go over them together. Okay, iodine has the symbol of capital I. It's a 1-letter symbol. What about iron? Iron is capital F, lowercase e. How about magnesium? Capital M, lowercase g. Zinc, ZN. Sounds pretty right. And nitrogen is capital N. Notice that iron, Fe, doesn't really relate to iron. It's actually based on the Latin name. Okay, for the next set of questions, give the names of the elements with the following symbols. So you'll have to use your periodic table to answer these questions. Take a moment, pause the video, and answer the questions on your own, and we'll come back and answer them together. Okay, P represents what element? Phosphorus. Al represents what element? Aluminum. Oops. Mn represents manganese. I did not spell it correctly. That should be spelled Manganese. H represents what? Hydrogen. And K represents potassium. Which, if any of these elements, are necessary for human life? Most of these, except for aluminum, are required for human life. Okay, let's do some more practice. Which of the following represent elements and which represent compounds? Pause the video and practice on your own, and when you come back, we'll go over the answers together. Okay, C represents what? It's an element, the element carbon. What about Cu? Cu is also an element. It's represented by that's a representative of copper. What about capital H, capital I? It's a compound. Remember, I said that if you see 2 capital letters next to each other in a symbol, then you know that it's a compound. How about capital B, capital N? It's also a compound. What about capital I? So let's say HI is hydrogen iodide. Bn is boron nitride. What is In? In we can find on our periodic table, and that is indium. What about the very last one? Capital H, capital Br. Well, I know that capital H is hydrogen, and then I've got another symbol with a capital letter and a lowercase letter. Well, that must be bromine. So this has got to be a compound, and then this is hydrobromic acid, actually. All right, here you go. Practice on your own. Pause the video, answer the question, and we'll come back with the answer. What is the chemical symbol for bromine? Well, the answer is C. Oh, let's go back. B is for boron. Be is for beryllium, and D is for bismuth. So the chemical symbol for bromine is Br. What element has the symbol Ag? Pause the video, answer it, and we'll come back and do the answers together. What's the answer, folks? A, silver. What is the symbol for gold? It's Au. How about the symbol for aluminum? Al. And what about the symbol for americonium? It's Am. Uh-oh, that wasn't supposed to happen. Well, here we go. Which of the following is an element? I've already given you the answer. NO. How do we know that this is the element? Well, it's got a capital letter and a lowercase letter. And the others have a capital letter and another capital letter in the symbol. So it's got to be representing a compound. Table salt is considered a compound. It's sodium plus chlorine. And if we were to break this down or decompose it, we'll end up with sodium and gas. Is sodium chloride the only salt you've encountered in daily life? If not, what are some others? So salt does not only mean sodium chloride. What about Epsom salt? What about calcium chloride that we use to ice our streets? Those are all salts, and we'll learn that salts are made up of elements that are metals and nonmetals. When we're doing a chemical formula, the symbols of elements are combined. Notice here that H2O, we've got 2 atoms of hydrogen and 1 atom of oxygen. CH4, we've got 1 atom of carbon, 4 atoms of hydrogen. C12H22O11 shows us that we have 12 atoms of carbon, 22 atoms of hydrogen, and 11 atoms of oxygen. This is actually, no, that's not glucose. It's a sugar, this representation here. So notice that a chemical symbol always is going to have the number of atoms present for each element that is within the compound. Notice that for 1 atom, we don't have a subscript. Let's practice. How many atoms of carbon are in 1 molecule of isopropyl alcohol, which has a chemical symbol of CH3 parentheses 2 CHOOH? Take a moment to answer this question on your own, and we'll answer it when you come back. The answer is 3. How do we know this? Well, I've got a carbon here, but notice it's surrounded by parentheses and a subscript of 2. So what that means is I have 2 carbons and I have 6 hydrogens in this parentheses. So 2 carbons plus 1 carbon gives us 3. We've already talked about matter in its forms of either a pure substance or a mixture, but let's take a closer look at matter, not looking at in terms of pure substance or a mixture, but let's take a look at the 3 forms of matter. So there are 3 states, or 3 physical states, or 3 forms of matter, main forms: solids, liquids, and gases. Plasmas are not included on this PowerPoint, but they are another state of matter. A change of state is a conversion of a substance from one state to another. We can convert between a solid and a liquid and a gas, or a gas and a solid. To do so, to go from a solid to a liquid is melting, and to go from a liquid to a solid is freezing. To go from a liquid to a gas is evaporation, and to go from a gas to a liquid is condensation. To go from a solid to a gas is sublimation, and deposition is going from a gas to a solid. What do you think causes substances to change physical state? Well, it has to do with each form itself. Gases substitute particles. Gases have substances that are with particles that are widely separated. They have no definite shape or volume. There's no interaction between the particles within a gas. A liquid, however, is a substance with particles that are close together. They're in motion. They have a definite volume, but they only take up the shape of the container that they're in. A solid has substance with particles that are very close together. They have a definite shape and a definite volume. Many substances can exist in all three phases and can participate in phase changes. But what actually keeps substances in either a solid, liquid, or a gas phase? Well, the change of state has to do with the amount of energy that is within a substance. So, as a solid, solids have very little random motion. We see that particles are really close together and they're very organized in a pattern. For liquids, particles are close together, but they're disorganized. There's still lots of interaction between them, and they're moving around pretty rapidly. Gases now completely fill a container, and their particles are really far apart. What is the difference between these things? It's only the amount of energy that is associated with them. Do you remember lining up in school in elementary school? Just imagine having children in elementary school lined up in the gymnasium ready for class. Well, we can think of a solid as those students all lined up nice and neat in their rows with their hands to themselves. They're waiting quietly and they're waiting for their teachers to come pick them up. Someone brings the whole set of students cereal with frosted flakes full of sugar. What is in that sugar? Energy. We give the kids a little bit of energy, and what starts happening? Well, sooner or later, kids start poking each other, pulling each other's book bags, pulling hair, and that can represent a liquid. As time goes on and they ingest more and more energy, they start running all over the classroom. They're bumping into each other. They're falling down, or they're in the gymnasium. They're running all over the place. They're falling into each other, and they're all in random motion. So that's a way to think of a solid, liquid, and a gas. You can click on this link if you are looking at this. If you download this PowerPoint on Blackboard, you can click on this link and see a simulation on the states of matter. So let's practice. Identify each description as that of a solid, liquid, or gas. Take some time to answer the questions. Pause the video, and when we come back, we'll answer them together. Okay, A, it has a definite volume but takes the shape of the container. What is that? It's got a volume, but it takes the shape of the container. Can't be a gas, it's got to be a liquid. Its particles are moving rapidly. Liquid particles are moving around pretty rapidly. However, gases are moving the fastest, so we can say gases are liquid. Its particles fill the entire volume of the container. Well, we know that liquids fill the container, but they don't fill the entire volume of the container. That would be a gas. Its particles have a fixed arrangement. Well, not in a liquid, not in a gas. It's got to be a solid. Its particles are close together, but they're moving randomly. Particles are close together, but moving randomly. Well, they're moving around, so it can't be a solid. It must be a liquid. Let's try this next set of questions. Identify the state of matter for each of the following. Take a moment to pause the video, answer the questions, and we'll come back and answer them together. Vitamin tablets are solids. Eye drops are or is a liquid. Vegetable oil is considered a liquid. A candle, not the wax, liquid wax, but a candle itself is a solid. And steam is only what? It's gaseous water. Please, I apologize about the siren in the background. All right. Take a moment, pause the video, answer the question, and we'll come back with the answers. Which of the following is the most compressible state of matter? All right, the answer is a gas. Why? Because solids, have you ever tried to squeeze a golf ball? Can you squeeze a golf ball? Nope, it's a solid. It's solid all the way through and through. So it's really hard to compress solids. Liquids can compress, but only to a certain amount. So the answer is gases. We will stop here and continue the rest of this lecture in class.